So let us start our lecture on parameter optimization for neural networks. First, we define the main mathematical symbols needed in this lecture. So the inputs of a neural network is called feature vector, and we use the symbol small x and define it to be a vector with little n components. This is a convention. Of course, we can have neural networks where we input matrices or higher dimensional arrays or tensors, but we can always formally reshape them into a vector with such a shape as here. Now, the dataset matrix is the set of such input vectors that we need, for example, to represent a batch or the entire training dataset. So we use the symbol capital X, and we have capital N rows in this matrix and little n columns for the different dimensions of the feature vectors. Now we assume we do supervised learning. So we have labels that we train the network to reproduce. The network has outputs, and we compare the outputs to labels, and we try to make the outputs and labels similar. Now there's for every training data point, we have a label vector called little y with L components, and we can assemble those into a label matrix with capital N rows and little l columns again. Our focus of attention are the parameters. So we use the symbol theta for denoting the parameters that we want to learn. We denote them as a vector with d elements. And again, this is just a convention. In practice, for a neural network, we usually have a set of parameters that each are arrays of different shapes and sizes, but we can always order them using some convention and put them into a long vector. Now, finally, the quantity we want to train or minimize is the loss or cost function. We use the convention to call it C, and it depends on X and Y, so inputs and labels, and the parameters theta. That's for supervised learning, and for unsupervised learning, perhaps we don't have Y as arguments in the loss function, we just have the inputs X. You can think of the cost function as a quantification how well a given model with parameters theta explains the observations X or X and Y. And what we want to do, we want to fit or optimize this model. So we want to minimize the loss function over the set of parameters. So we want to find the parameters which minimize the loss function. Minimizing and maximizing are exchangeable. So usually we speak of loss functions, and then we want to minimize them. If we have a function like a score function that we want to maximize, we can equivalently minimize minus that function. Now, the difficulty of finding the minimum depends very much on the shape or the form of the loss function. If our function is linear or can be linearized, then we can use simple linear algebra methods to find the solution, so the optimal set of parameters directly. We have seen this in linear least squares regression. For neural network functions and the loss functions defined on their outputs, this is generally not the case. These are complex, nested, nonlinear functions for which we usually cannot write down directly an expression for the optimal set of parameters. So we need to find the parameters iteratively. We need to gradually improve them in order to reduce the value of the loss function bit by bit. And the basic technique for doing this is gradient descent. So we compute the derivatives of the loss function with respect to the parameters. So the gradient of the loss function with respect to the parameters. And then we move the parameters into the direction where the loss function decreases. So we move it into the direction of minus the gradient of the loss function. Gradient descent has to deal with several difficulties. So the most important difficulty is that such loss functions are often non-convex and they may be rugged. So that means they can have many local minima. And when we start somewhere from an initial set of parameters, we may just get stuck in a local minimum by minimizing the loss function with respect to the parameters. And we may not find a good local minimum or even the global optimum. Then specifically for machine learning, we often have loss functions defined on data. For example, in supervised learning, we compare the predictions of a neural network with the labels for that corresponding data point, that we have an expression for each data point, or we have a term for each data point. So that means the loss function is very expensive to evaluate. We need to do a lot of computation to compute the value of the loss function for the entire training set. And finally, also for machine learning, one of the difficulties is that the exact loss function is often not available. We have defined the loss function on data, so we have a given set of data and compare, for example, labels with predictions. But that doesn't mean this is the exact loss function. It's just a sample of the loss function, assuming that the data comes from a certain distribution and we only see a part of this distribution. So that means the loss function that we practically use is defined by this particular data sample that we employ. So if we repeated the process of generating the data, of let's say doing an observation which produces the data many times, then each time this defines a different loss function. And of course, the hope is that if we do that many times, then the general shape of the loss function is similar. So the locations, the parameter values where the loss function is small are similar, or they lead to similar predictions, but not every local minimum of the loss function is meaningful. Actually, many of them are just results of having, for example, too little training data. So we want to avoid optimization procedures that are very prone to get stuck in local minimum. All right, here are a few references for further reading. This is a good starting point for learning about gradient descent, stochastic gradient descent, and backpropagation. So we will not use plain gradient descent because we do not want to get stuck in every little local minimum, but we need to understand it in order to build upon it, to build more complex optimization methods on it. So let us look at what gradient descent does for such a simple quadratic function here sketched in blue in the top graph. The gradient of this function is just a one-dimensional function, in this case the green line. And since we optimize by going towards minus the gradient, that means we will just go to the right if we are on the left side of the graph, or if we are at negative values, and we will go to the left if we are at positive values. So we'll move towards this point of x equals 0, y equals 0 of the function. At the optimum, the value of the gradient is 0, but note that this is not only true for minima. So in fact, it is true for minima, for maxima, and also for saddle points. And that is a crucial point, especially for high-dimensional functions. Remember that when you optimize a one-dimensional function and you want to check whether you have found a minimum, a maximum, or a saddle point, then you need to look at second derivatives. If the second derivative is positive, you're in a minimum. If it is negative, you're in a maximum. And a hallmark of the saddle point is the second derivative being 0. Now, this is for one-dimensional functions. In multidimensional functions, we need to look at the eigenvalues of the Hessian matrix of second derivatives. For a minimum, all eigenvalues are positive. For a maximum, all eigenvalues are negative. And for a saddle point, we can have a mix of the two. Now, following simple statistical arguments, it is simply such that minima and maxima are rare things in high dimensions because you need all the eigenvalues to be negative or positive. So that means saddle points are much more common in high dimensions, and they are the most frequent stationary states, so the most frequent states where the gradient is 0. So in other words, if you are doing gradient descent in a high-dimensional function, you will often find saddle points and get stuck there unless your method is somehow resistant or safe against getting stuck there. So this is an important criterion to think about when designing a parameter optimization algorithm for neural networks. All right, gradient descent, let's just do it formally as an algorithm. So first of all, we abbreviate the loss function as c of theta, so we just omit further arguments because simply we're using it a lot. And the simple gradient descent algorithm is as follows. We initialize the parameters with an initial parameter vector theta 0, and then we do t time steps or t iterations, or iterate until some convergence criterion is met. For example, until the value of the gradient is below a certain threshold, so until the norm of the gradient is below a certain threshold. So first of all, we compute the gradient by taking the derivative of the loss function with respect to the parameters. This in neural networks is usually done with the backpropagation algorithm that we have introduced in the last lecture. And then we update the parameters by changing them a little bit in the direction against the gradient. So by taking theta t and subtracting eta t times the gradient, whereas eta t is the learning rate. And the learning rate controls how big a step is that we take into the search direction of minus the gradient at a given iteration or time t. Now for a small learning rate, this method will converge to a local minimum of the loss function. But of course, small steps means we have to do many steps to get there, and that means a large computational cost. For large learning rates, this is a little bit dangerous because the algorithm can overshoot the minimum and even diverge. So it can actually get worse and worse in every step and get towards increasing loss function values. In practice, the learning rate eta is chosen adaptively or simply decreased over time. So you have some sort of algorithm which controls the value of the learning rate, because very rarely you know in advance what the right learning rate or the optimal learning rate for a given problem is. This slide illustrates the role of different learning rates. So in panel A, you see a small learning rate. So we start from an initial parameter set, we do little steps, and we eventually end up at the minimum. But we need many steps to go there. In panel B, we were lucky. We have chosen the exact correct learning rate, so we go to the minimum in one step. In practice, we can usually not reach the situation, but of course we want to be close to the situation, as close as possible. In panel C and D, you see what can happen if the learning rate is too large. So in panel C, the learning rate is above the optimal learning rate, and we still converge, but we waste a lot of time by jumping back and forth around the minimum. Whereas in panel D, the learning rate is so large that we actually every time make a bigger and bigger step, and we eventually diverge. So we leave the minimum rather than going close to it. So what is the optimal learning rate? Well, before answering that, we will first consider a more general optimization method, namely a second-order optimization method, Newton's method. This is generally not a method we want to be using for neural networks, but we can learn something from it for gradient descent. In order to derive Newton's method, we do the following. So we first represent our function that we want to optimize as Taylor expansion to the second order. So we say we expand our loss function around the parameters theta by asking how does it change if we add a vector v to this theta parameter, and then representing this function by a Taylor expansion, which we stop at the second order. So what do we need for that? We need the value of the function of the loss function itself at the parameter set theta. We need the gradient at theta, and we need the Hessian matrix of second derivatives at theta. And then together with the vector v, we can write down the expression of the second order Taylor expansion around C of theta. Right, so this is basically a model of our true loss function C. This is an approximation to the loss function C, which is valid close to the parameter vector theta, so if we don't go too far away from it, and it's the best approximation we can get by using derivatives up to the second derivative. Now we assume this model is exact. We use this model instead of our original function, and we ask the question, what do I need to do to find the optimum, the local optimum of my model function, of my second order Taylor expansion of the original function, if that is really the true function. And that can be done by taking the Taylor expansion, taking the derivative, and setting it to 0, and then we'll see what we get. And what we get is this equation. So that says the gradient at the parameters theta plus the Hessian matrix at parameters theta multiplied with the vector v equals 0. We have to satisfy this equation. So what has happened here is that we are asking the question, what is the displacement vector v or v opt, that if we use it, if we go this step away from theta, makes the gradient of C 0. And in order to answer this question, we have used not the original function C, because with the original function C we cannot do that, but we have instead used the second order Taylor expansion for it. And then in order to answer this question, we just need to solve this equation. So we need to find V such that this equation here is true. So we solve it by just rearranging it. We get the gradient to the other side. We invert the Hessian matrix, and then we have an expression for the optimal V step. And so this is the optimal change of parameters from the point of view of a second order Taylor expansion. This will directly get us to the next critical point, the next point of gradient 0. And this is Newton's method, or the Newton update in second order optimization. So a technical remark, often the Hessian matrix is poorly conditioned, so it may have many eigenvalues close to 0 or even eigenvalues identically 0. So in this case, we cannot just invert the matrix directly, but we often replace the inverse by a regularized inverse. So we actually use the inverse of the Hessian matrix plus a small multiple of the identity matrix with a small parameter epsilon here. This is something that should look familiar for you. In linear least squares regression, we have done something similar, and that was called ridge regression. So in ridge regression, we regularize the covariance matrix that we also need to invert in order to find the optimal parameters of a linear least squares problem. And we regularized it there by also adding a small multiple of the inverse. And this is also called a shrinkage estimator of the covariance matrix. Yeah, it's the same trick here. We don't call it shrinkage estimator. It's simply a regularization of the Hessian. So in neural networks, I mentioned that we do not want to use Newton's method directly, and this is simply because we have a lot of parameters. So the space over which we want to optimize is simply very large. For example, we may have 1 million parameters or even more, and then Newton's method would entail computing a Hessian matrix, which is 1 million by 1 million, which is huge. It's too hard to store it, and also then inverting it, so computing the matrix inverse, which is dimension to the third power, is simply unfeasible. However, we can learn something from the Newton update for gradient descent, and for that, let us look at one-dimensional functions for now. So let us look at this simple harmonic function as a loss function. The gradient is then simply k times theta in this case, and the Hessian matrix is simply equal to k. It's just a scalar. And inserting those results into the Newton update leads to the following update. So we update the parameters by adding a step of minus k inverse g and g is again k theta. So of course, because this is just a quadratic function, so it only has second derivatives, Newton's method will immediately find the optimum. So as you see, you immediately go to theta t plus tau equals 0 with this update, but you can just compare this form of the update to gradient descent. And then you see that our learning rate now is k inverse. So k inverse has become the learning rate. And that tells us if we are in a situation like this, where we have a locally harmonic function, then basically we want to take a step size or use a learning rate which is like the inverse of the stiffness of the potential. So in other words, for very stiff potentials or for very stiff loss functions, we have large k's, then we need to make small steps. Whereas if the potential or the loss function c is very shallow, we can make large steps. Now we can follow a similar argument for multidimensional cases, and I'm not showing you the derivation here explicitly, but you can show that for multidimensional functions, the optimal Newton learning rate is just the inverse of the largest singular value of the Hessian. Yeah, so you take the Hessian matrix of second derivatives, its singular values or eigenvalues, which is the same in this case because the Hessian is a symmetric matrix. So they tell you something about the curvatures, about the different magnitudes of curvatures in different directions. You can obtain the singular values with this singular value decomposition. So this is a standard linear algebra decomposition method that is available in NumPy, MATLAB, and many other linear algebra packages. And when you have computed the singular values, you take the maximum singular value, and its inverse determines the step size for gradient descent, or the optimal step size for gradient descent, motivated from the Newton update. But you can already see that this is kind of a very pessimistic update. So in high-dimensional systems, we have many singular values. You take the largest and you invert it, and that tells you what the step size is. So that basically means for high-dimensional systems, your optimal step size is almost always very small. So how long does it take until we converge to the next local optimum? Well, that depends on the ratio of the largest and the smallest singular value. The largest singular value basically tells us what is the stiffest direction in this multidimensional space, and that tells us how large is the or how small must the update or the step size be with which we move. But the smallest singular value, that tells us what is the shallowest direction towards the optimum, and that tells us how many of these steps we need to make in order to get there. So it's really the ratio of these two numbers, and that can be very large. And if that is very large, then that means we have to take a lot of steps with gradient descent in order to find the minimum. And the ratio is large for very anisotropic minima. So in other words, if there's one direction where the curve is very shallow and one direction where the curve is very steep, then you have a very anisotropic minimum, and you just do many small steps with gradient update in order to get to the minimum. So this is actually a case where gradient descent is quite bad or converges very slowly. So summing up, actually we have now discussed a lot of problems of gradient descent, and of course we want to try to improve on them and find better methods that have less of these problems. But let's just summarize. So gradient descent finds local minima of the loss function. So a disadvantage of that is that the optimization may get stuck. So what can we do? Well, we can use some perturbations. We can add some noise, some randomness, some stochasticity in order to escape local minima. That is one idea we will follow up on. Related to that, because gradient descent finds local minima, it is sensitive to the initial condition, so it depends very much where we start with the initial parameter vector. And what can we do there? Of course, again, use stochastic perturbations, but also try different initial parameter settings. So run gradient descent from different starting points. A practical consideration is that the loss functions we want to optimize are often of this form. So it's a sum over data points of loss functions for every single data point, such as in supervised learning, where we compare predictions of a neural network with the labels of the corresponding data point. And in this case, computing the loss function and also the gradient of the loss function is expensive because we simply have to evaluate many, many terms. But up to a prefactor, this form looks like an expectation value, like a mean value over many data points. So, and therefore we can, instead of using the whole expression for the expectation value, say we just use a subset of data points. So we compute a sample expectation of the gradient. That leads us to stochastic gradient descent. As we have already noticed, gradient descent is very sensitive to choosing the learning rate eta right. And if we choose the learning rate too small, we may have to make many steps. If we use it too large, we can diverge. The loss value can increase instead of decrease. And therefore, we need to think about what we can do in order to choose it adaptively. So we need to seek adaptive algorithms for the learning rate. We have just discussed gradient descent is bad for anisotropic minima. So its problem really is it uses the same learning rate in all directions, but it would be better if it had different learning rates in different directions of the space. So of course Newton method does exactly that. It uses the inverse of the Hessian matrix in order to choose different step sizes into different directions. But as we said, inverting the Hessian matrix is too expensive in high dimensions. So we need to find other ways where we can do something similar, where we can make large steps in directions where the function is shallow and small steps in directions where the function is steep, in order to avoid overshooting the minimum or diverging, but also avoiding taking a huge amount of steps in order to get close to the minimum. And then finally, pure gradient descent gets stuck in all kinds of critical points or all points of zero gradient, including saddle points. And high dimensional functions have many, many saddle points. So we need methods that can get unstuck in saddle points, or that can essentially still make progress even if we're in a saddle point, but not in a local minimum. All right, so now we are done with the gradient descent part of the lecture. And now as a next step, we will introduce stochastic gradient descent, which will resolve some of these problems listed on this slide here.